Welcome to Get Your Wings, Aviation Meteorology Bites Lapse Rates. There are three kinds of lapse rates that we will be looking at. The first is the dry adiabatic lapse rate, followed by the saturated adiabatic lapse rate, and lastly the environmental lapse rate. Before we do, we will renew our understanding of dew point. Dew point is the point at which, due to the drop in temperature, the contained water vapour in a parcel of air begins to condensate, changing from vapour back to liquid, and in doing so it will release some latent heat. At the dew point temperature, the air parcel is saturated and thus can hold no more water vapour. This is the point in the atmosphere where clouds will start to form. Dry adiabatic lapse rate, DALR. In unsaturated air, this is the rate that a parcel of air rising from the Earth's surface will cool. The dry adiabatic lapse rate is 3 degrees centigrade per 1,000 feet. In the Earth atmosphere, the air is seldom completely dry. It is usual for it to contain water vapour. So in this context, the word dry refers to a relative humidity of less than 100%. As you can see in the diagram on the right, the parcel of air will ascend and lose temperature at the rate of 3 degrees centigrade per 1,000 feet until it reaches the dew point. Saturated adiabatic lapse rate, SALR. As we've seen, an unsaturated parcel of air will rise from the Earth's surface and cool at the dry adiabatic rate of 3 degrees per 1,000 feet until it has cooled to the dew point. Because of the release of the latent heat at the dew point and above, the rate at which it cools is lessened to 1.5 degrees centigrade per 1,000 feet, and this is known as the saturated adiabatic lapse rate. So as you can see in the diagram on the right hand side, initially the parcel of air will ascend, and as it does, it will lose temperature at 3 degrees per 1,000 feet, the dry adiabatic lapse rate, until it reaches to the dew point. At the dew point, due to the process of condensation releasing latent heat, the rate at which it cools will now be 1.5 degrees centigrade per 1,000 feet and is known as the saturated adiabatic lapse rate. Environmental lapse rate. The environmental lapse rate is the rate at which the air is cooling in any given circumstances. So this is the actual lapse rate for the day when you're looking outside and you're seeing how much it cools by. However, in aviation, when we use the term environmental lapse rate, we are concerned with the ICAO, standard atmospheres lapse rate. And the ICAO, the International Civil Aviation Organization's standard atmosphere, quotes the environmental lapse rate as 1.98 degrees centigrade per 1,000 feet. We normally round this to 2 degrees centigrade per 1,000 feet for ease of working. So we can say for every 1,000 feet we ascend in an aircraft, we can expect the temperature to drop by approximately 2 degrees centigrade. We can use the lapse rate to predict whether the air will be stable or not. Stable air, a layer of air having a temperature change, i.e. lapse rate, of less than the dry adiabatic lapse rate, 3 degrees centigrade per 1,000 feet, will be considered as being stable due to the retarding of upward or downward mixing. By checking the 214 on the Met Office before we fly, we can ascertain whether the temperature difference in the altitudes at which we intend to fly will be less than the dry adiabatic lapse rate and therefore stable air, or more dry adiabatic lapse rate and therefore unstable air. We can also look at other clues. If we look at the clouds, if they are flat, then they have been formed in a stable environment and are known as stratiform. If the clouds have been formed in an unstable environment, they are often puffy with good vertical development, known as cumuliform in an unstable environment. Temperature doesn't always decrease with altitude. and this is known as a temperature inversion. A temperature inversion is simply where temperature increases with height. This often happens in areas of high pressure, where the air higher up starts to sink down. As it falls, it dries out and warms up. This warm layer of air can act as a cap, trapping cooler air beneath it. If we look at the Föhn effect, which in simple terms, the Föhn effect is the change from a wet, cold conditions on one side of a mountain to a warmer, drier conditions on the other side of the mountain, known as the leeward side. So the air coming from the windward side is pushed up and cools at the dry adiabatic lapse rate until it reaches the dew point. It then continues to cool at the saturated adiabatic lapse rate, creating clouds, possibly rain and other weather phenomena. And then as it goes over the top of the mountain, the descending air warms all the way down at the dry adiabatic lapse rate, creating temperature difference between the windward and leeward side, and the leeward side being a warmer, drier environment. Hopefully you've found this interesting. If you have, give me a like and a follow for more content. Thank you.